There's an integral so elegant, so mysterious, it pops up anywhere, from physics to probability to quantum mechanics. It's called the Gaussian integral, and it looks like this. This integral defines the shape of normal distribution, aka the bell curve. It's why test scores cluster around an average, why errors in measurements behave predictably, why the universe has a most likely outcome based into randomness. And its answer? This is it. Not an approximation, not coincidence, just pure math magic. With something so simple, one has to beg the question, how did it come about? There's a guy behind this integral called Friedrich Gauss. At just 18, he studied the bell curve while analyzing astronomical errors. Later, he showed it was the curve that nature seemed to favor for randomness. No other function fit better. This one integral ties together probability, physics, statistics, and the structure of the universe itself. Our idea comes from this area underneath this curve. If we were to find the area, we wouldn't be able to find it just using regular calculus or the type of calculus that we learn in Calculus 1 or Calculus 2. So what we have to do is reimagine this integral I as I squared, where you have two different integrals being multiplied together, giving you this result right here. Now, if you know anything about double integration, you know that this represents the volume of a three-dimensional surface. This three-dimensional surface expands the entire x and y plane. So now you're trying to take the volume of this surface as x approaches from negative infinity to infinity, and y also approaches from negative infinity to infinity. Now, this formula right here has something very unique to us, or something that we can generalize, and that's polar coordinates. And if we're trying to find the volume of the 3D shape that we're talking about, r is going from 0 to infinity as it goes on forever, and theta is just going to go from 0 to pi over 2, wrapping around the entire x and y coordinate plane. Now, using this relationship here, we can rewrite our I squared in terms of r and theta. Then we do the first part of the integral problem in terms of theta, giving us this value right here. We implement the first fundamental theorem of calculus, and there's our answer. Then we use a simple u substitution where u is equal to r squared. You find your differential, then you change your parameters as r equals 0 and then as r approaches infinity. We get this integral right here, giving us I squared is equal to pi. Now, we need to find I in this particular problem, so all we have to do now is just take the square root, and we get that I is equal to the result that we had talked about initially, which is root pi. One simple curve, one radical result. The area underneath the curve e to the negative x squared from negative infinity to infinity is the square root of pi. And that is what we call the Gaussian integral.